All right, I think we're live right now. Yeah. All right, so I'm going to share this screen with you, and again, I'll point out that we are at the lesson on substitutions. I'm going to review those. They were not on the quiz, so this is kind of like almost like a new subject. So let's go ahead and let's review them. So we're looking at section 4.5, the substitution rule. All right, and that is so as I told you, I'm going to do an example here, and I'll explain on this example. So we'll do number 6 of section 4.5, and this problem is the integral of square root of 2t plus 1 dt, u being 2t plus 1. All right, so what is this problem about, folks? And what's up with this substitution? Again, if you forgot, well, this is a good time to review these quickly. So here's what it is, folks. So if somebody gave us the antiderivative of square root of x dx, we would know what to do. We would say, oh, that's the antiderivative of x to the 1/2. It's a power of x, and we did that on the quiz. So you can continue here. But we don't have that. So we have something more complex. Instead of square root of x, we have square root of 2t plus 1. So forget about this thing, which actually is part of a correct solution, but it's not coming up right away. So what people would do, they would substitute the formula in here. They would call this one the new x, or u in my case. So that's called the u substitution. So we replace part of this formula by something that makes it easier. But now, why is this formula easier? Because if I calculate, so remember, you have to replace not only 2t plus 1, but also the dt here. If I want to calculate this thing here, I would have to also change the dt, and that's the problem here. So we're going to say, you know what, the derivative of u, remember the last time I explained how this is derived from the chain rule. So that's in the chain rule, that's there's a derivative always at the end. So if you have u to the, I don't know, 3/2 primed. So that's going to be 3/2 u to the 1/2 times u prime. Well, that's the thing here. So that's why we need to do this du. This plays that role of the new variable in the formula, and this du will be 2 dt. So remember 2, why? Because it's the derivative of u, so u prime is 2. And then we say dt because, the formula over here on the right side is in t. That allows me to replace the parts of this formula as follows. So we're going to say the antiderivative of square root of u, which is 2t plus 1 here, as I said. And then we have to take care of dt, which is dt from here is simply, if you solve for dt, you'll get dt, well, that's 1/2 du. So divide by 2, right? So this is going to be times 1/2 du. And of course, you rewrite this nicely, 1/2 square root of, well, instead of square root of u, we just said we would write u to the 1/2, right? So 1/2 u to the 1/2 du. And that is a simple antiderivative. So at this point in time, remember these two symbols form an antiderivative. And the antiderivative of 1/2 u to the 1/2 is 1/2 times u to the 3/2 times 2/3 over here. And these two simplify and we'll end up with 1/3 u to the 3/2, which is not the final answer. Remember, we need to always put the answer in terms of a letter you start with. So this is going to be 1/3 times u, which is 2t plus 1 to the 3/2. All right, folks. So that is the antiderivative. If you want to be fancy, you can put a c at the end here. It doesn't have to be. All right, folks. So this is the answer to this particular problem. All right, and now this being the necessary review, let's kind of take a look at what happens here. So here's what happens, folks. We have a problem that is of the following form, so type of this problem. It's the antiderivative. Something, something here, some formula in X or in U or something like that in X, right? I'm not going to say what the formula is because again, it's unimportant. So what's important here is that this is to a certain power, let's say to the third or 1/2 or something like that, and then we have times dx over here. So this in here is some formula in X. Let's say a u of X or something like that. And so this is the type of problem that we're solving. And we also know that the derivative of u usually is something that that is easy to evaluate in X. So it would be something like maybe 4dx or something like that. And then we would replace the dx from this formula, from the derivative, and then we would replace this quantity here by the substitution we made. So that's kind of a style of problem. Now this problem can get a little more complex. Let's say we have times some other quantity here, which again, I'm not going to specify, but the trick should be that whatever your substitution is, this u prime guy should be this missing thing here. So that should be u prime. Otherwise, your substitution doesn't work. All right, so this is the type of problem that we do in Calculus 1. Now, I was telling you that the difference between Calculus 1 and Calculus 2 is that in Calculus 2, you see a variety of other problems where you can apply the substitution rule. Unfortunately, in Calc 1, this is kind of the main thing, really. So every single problem that we will see here will follow this particular pattern, will be some power of some formula times the derivative of that formula. So the type of problem we see here, we see in Calc 1 is the antiderivative a power of some function times the derivative of the function. All right, dx. So that's the style of problem that we will see here, and we always so I shouldn't even put quantities here. So there we go. So power times the derivative. All right. So we always have to figure out this power properly, and then pretty much that's the u substitution. So that gives you the u substitution here. Is this function whose power is calculated here in the integral. All right, folks. So that being said, I am going to show you that really most of these problems here are of that type. There's nothing really intelligent. So in Calculus 1, you can basically survive with just one type of problem. Actually, maybe two, because we'll do another one. But there's just no variety. And the situation is different in Calc 2, where you have to do a bunch of other types of substitutions, and you have to do more sophisticated things. All right, so keep in mind this example. This is really the example that we're gonna focus on time and time again. And I'm gonna move pages, but I'll come back to this page. This is page 2. And I'll show you time and time again, this is the type of problem that we deal with. So let's do number 7, and let's see how number 7 is that type of problem. section is 4.5, obviously. So this is the antiderivative of x square root of 1 minus x squared dx. All right, folks. So so what we have here is, again, well, do we recognize the power of a function times something else? Yes. Here it is. So it's kind of hidden here in the problem. So let's rewrite this as the integral of 1 minus x squared to the 1/2. This is the power we're looking at, folks, times x dx. All right. So this is going to be the power. So it's here. So this is likely going to be our substitution of the power of this function. So that will be my substitution. So I'll say here, let's choose. Again, it's not a 100% recipe, so it might be that it doesn't work, but we'll see. So let's choose u equal to 1 minus x squared. Well, if that's the case, then we're going to say that the derivative of that du is negative 2x dx. So, so look here, folks, this x dx really, you see that here? So x dx is almost there. It's not entirely here, but it's matching up to a constant. So x dx can be really found out. So if the derivative is negative 2x, but I can figure out x simply by dividing by negative 2. So negative 1/2 du is over here. So so what we get here, folks, is this integral, is the integral of, or actually, well, I should say that one here, because that the first one is not necessarily particularly helpful. The second part is u to the 1/2 times an x dx is just negative 1/2 du. So so these, folks, is equal to, and right now we are going to say, well, that's the antiderivative of negative 1/2 u to the 1/2 du, and that is negative 1/2 times, and for u to the 1/2, again, the antiderivative, we already did that, 2/3 u to the 3/2 in the previous problem. So this ends up being, folks, the final answer is negative 1/2 times 2/3. That's going to be negative 1/3 times 1 minus x squared, folks, to the 3/2. That is the antiderivative, Odyssey, if you want it as the final thing. So that is the antiderivative for x square root of 1 minus x squared. And I hope everybody, again, everybody understands this is just that one pattern, folks, that we beat down, until we really figure out how that works. So this is the pattern that we will drill today. So that's one problem. Again, if you notice here, so power sum function derivative. There we go. So there's the power, there's the derivative. So a derivative up to a constant, I should have said, but you get the idea. Derivative of 1 minus x squared is negative 2 times x. So so there we go. That's the derivative. All right, folks. So so I'm going to go to the next page, and I'll do another problem. Right now, by the way, throughout the lesson, you can really keep stopping the video if you watch it. Stop the video, do the problems yourself, and then see how I do them. All right. So number 9 of section 4.5. Integral 1 minus 2x to the 9 dx. All right, so this is the antiderivative. Now, what do we do here? So again, let's do the substitution. So it's a power, it's everything is fine here. So we just have to do the substitution as 1 minus 2x, and we will see that the du is negative 2, right? Negative 2 times x prime is 1, negative 2 dx. All right, so this is the change of variables, and this is equal to the antiderivative of 1 minus 2x to the 9. All right, so it's u to the 9, and instead of dx, we're going to say, look here, folks, instead of dx, you're going to say dx equals negative 1/2 du. All right, so negative 1/2 du times negative 1/2 du, and that is equal to the antiderivative of negative 1/2 u to the 9 du, which is equal to negative 1/2 times u to the 10 times 1 over 10. So this is going to be negative 1 over 20 u to the 10, or if you want, negative 1 over 20 times, instead of u, I'm going to put 1 minus 2x to the 10. There we go. That's my answer. I don't have room to put the c, but that's okay. Without the c is fine as well. All right, so this is, again, yet another example of a power times the derivative. The derivative is hidden here, is the constant 1. As you can see, du is negative 2 times 1. So, you know, it's there. It's in the formula. So this is the second example of such type. All right, number 19. I'm going to do number 19 here. So there's going to be a bunch of problems like this one here, folks, number 19 of section 4.5, and that's going to be the antiderivative of x squared plus 1 times, and over here, x cubed plus 3x to the 4. dx. All right, so what do we have here? So, well, here's what we have. All right, so here's what we have, folks. We got this power. Do we recognize the power? There we go. So there's the power right here, x cubed plus 3x to the 4. So the substitution will be x cubed plus 3x. Again, if you have a chance to watch this again, stop the video and try this again at home. These are problems from the homework, by the way, folks. Du, the derivative is 3x squared plus 3. And that's going to be times dx. Now, do I recognize a missing part? By the way, here I forgot to write this again. So x cubed plus 3x to the 4 times x squared plus 1 dx. So do we recognize this part here as the derivative? Yes, we do, because this is simply 3 times, if you factor 3x squared plus 1 dx. So there we go. There's x squared plus 1 dx, the one here. So so that's du, and we can say, you know what, x squared plus 1 dx again is x squared plus 1 dx is going to be 1/3 du. So this is going to be equal to the antiderivative of u to the 4 times, and over here, instead of x squared plus 1 dx, we're going to put 1/3 du. And that's going to be equal to 1/3 the antiderivative of 1/3 u to the 4 du, which is, I just rewrote things, just move things around here, which is 1/3 times u to the 5th times 1/5. So this is 1/15 times the quantity x squared plus 1 to the 5th plus a constant c. So that takes care of my problem here, problem 90. Okay, folks. So, so we did a bunch of problems here. There's 1, there's 2, there's 3, and there's 4, the first problem. So all these problems, as you see, they all follow this pattern: power of some function times the derivative of that function. Now, let me go ahead and let's do something else. So let's do another problem that might appear to not look like that, or maybe it does look like that. Let's see. So here's what we have, folks. Let's go back and let's look at number 10. So you might say, wait a second, you're trying to confuse us. You said there would be one pattern, but number 10, if I'm looking here, 4.5, the antiderivative of sine t times the square root of, what is that, 1 plus cosine t dt. What in the world does this have to do with what we just said? What is the power? What is the derivative? Where is it? Well, if you look carefully here, this is the same type of problem, except that it's got some unusual type of things in there. So this is the power of 1 plus cosine t to the 1/2, that's the square root. And then it's times sine t dt, which is, just moving things around here in the formula. So I don't really do anything intelligent here, but I'm just trying to explain you that this is truly that same, the power, and this would be the derivative. Is that truly the derivative? Well, let's see. Let's see if that is the case. Yeah, it is the case, folks, because this is just 1 second. I'm losing my thing here. So what is that thing? Oops, I apologize. It pops up somewhere else. So see, the derivative, I didn't write that. I wrote the derivative and somehow didn't pick up. So the derivative is here, the derivative of 1 plus cosine. You see, that's sine. It's not quite sine, it's negative sine, but up to that constant, that's the one. So this is the exact same pattern as the one earlier, and this is going to be the antiderivative of let's say here what we do. U equals 1 plus cosine t, du is negative 1 times sine t dt. All right, so this is cosine prime d that, remember, is negative sine. So we do have, look at that, sine t dt. You see that? It's right here. It's just negative du. So sine t dt is negative du, and that is, folks, that is here the integral of and now we substitute, so right, 1 plus cosine t is u, so u to the 1/2, oops, hold on a second, times, and then sine t dt is going to be negative du, and that is going to be, folks, minus, okay, well, the antiderivative of negative u to the 1/2 du, and that is negative 1 times u to the 1/2. The antiderivative is u to the 3/2 times 2/3, and then that's negative 2/3 times 1 plus cosine t to the 3/2. And that's the final answer. I'm not going to bother you with that constant. If you want, you can put plus a constant here, but that's not important. So, folks, this is the antiderivative. And again, it's the exact same type of problem. It's just cleverly disguised with these trigonometric functions. And I tell you what, you will see such things in calculus too. But unfortunately, really here we focus on this one particular type of problem, and it's not so common of an appearance in calculus too. That's what I'm trying to say. So this is a problem that is still of the same pattern, a power and times the derivative. So again, keep in mind, this is the power times the derivative, right? So that's the that's the thing that you really have to keep in mind. So do I notice a power? Do I notice a derivative? Well, that's the case of a substitution if that's my antiderivative there. All right, so I'm going to move on to a new problem, and we will see that this is yet again, the same type of problem. All right, so right now we're gonna say um, the following thing. And you can see here there's a few things like that. So let's see. Let's do this number. This is interesting. It's slightly different in appearance, but you will see how the pattern is exactly the same. So number 17 of section 4.5 really is the antiderivative of secant squared theta times tangent cubed of theta d theta. Now this is a bit of a trick question. So to guess the correct substitution, you have to ask yourself which one is the power and which one is the derivative. So because both of them will appear to be powers, right? So what do we think about here? And if you're very careful here, you will see that there's one answer, one very clear answer. The derivative, folks, the derivative of tangent is secant squared. So that is the trick here to so all these problems, please think of them in advance, before you start writing. I see a lot of people. So when I used to used to teach in face-to-face in class, so I gave this kind of problem, and students immediately would write, oh, so this is a substitution, and they would choose u equals secant theta, and then struggle here, and it doesn't work. So don't just jump on the problem right away. So kind of look at the problem and inspect and see which one would be more appropriate. Would it be tangent or would it be secant to choose as my substitution? So I'm going to write the problem here. I'm going to write it this way to be more illustrative. So tangent cubed theta secant squared theta d theta. Oops. Sorry about it, folks. The theta. So see that? Oh, what's happening here? All right, so that thing popped out, and kind of scribbled here on the screen. All right, so folks, so we said that we choose our u substitution to be tangent theta. So this is the power, and this is the derivative, folks. And if u is tangent theta, then du is secant squared theta d theta. Remember, it's got to be d theta because it's the letter here. So really, you see that here, it's just the derivative right away. So this is going to be, if you calculate this is going to be u cubed, u is tangent, right? Times, and secant squared theta d theta is du. So it's as simple as saying 1/4 u to the 4, or if you want, so no more du here, so 1/4 times, and u was tangent, so we can say tangent to the 4 theta plus a constant c if you want. All right, let me just write this nicely here. So this is tangent. There we go. So 1/4 tangent to the 4 theta plus c. All right. So this is the derivative of that, the antiderivative there. So it's over here. So you can see that folks, if you look carefully here, really what we're looking at is a sequence of problems, and all these problems really are problems where the pattern is there over and over again. So it's always a power times a derivative. Are there any other types of problems that we see here in calculus? Yeah, there are. So by the way, number 23 is going to be the exact same type of question. Number 24. even number 26, 25, so all of them. Now, there's one type that doesn't quite fit this pattern, and that is number, and I noticed a couple of questions like that, number 11, number 15, number 16. So there's a few problems that don't quite fit this pattern. And here's one example. So I'm going to do, this would be type 2 here. So would be problems like this, like number, and I said number 15. And we'll do number 11 later. All right. So number 15 says the following thing of section 4.5. So it's the antiderivative of cosine of 1 plus 5t dt. All right, so this is the problem that doesn't fit the pattern we described earlier. It's not a power, not a power. However, you could in calculus 2, you will learn techniques to make this one look like a power of 1 plus 5t, but right now it's not. And what do? So here's the second technique, folks. When you have a trigonometric function and the argument of that trigonometric function is something complex, so you're looking at the following situation. You're looking at saying here, you know what? Let's make the argument of a trigonometric function into our substitution. Now, why is it that we didn't make in the previous problem over here? Why is it that we didn't make the argument our substitution? Because there was no complex argument there. So our argument was simply theta. Theta is simple enough. It's not theta plus 1. It's not 3 theta minus 7. It's not theta squared plus 7 theta. So none of that. It's just simply it's as simple as possible. So that doesn't trigger this kind of substitution. However, when you have things like this cosine of 1 plus 5t, that the argument of a trig function should be your substitution. So the second type I'm going to say on the next page would be to do something like this: u equals 1 plus 5t, the argument of cosine. So du is equal to 5 dt, and that's the thing that I do here. So this is equal to the antiderivative of cosine u, and over here instead of dt, folks, you see we don't have a 5. But we really have it here because it's a constant. It's a constant times 1, so it's a bit disguised here. So dt is going to be 1 over 5 du. And this is going to be cosine u times 1 over 5 du. All right, here, folks. So this is going to be equal to the antiderivative of 1 over 5 cosine u du. And that's going to be equal to, and this is 1/5 times the antiderivative of cosine u is let me say that directly. Why would I say integral? The antiderivative of cosine u, folks, is sine u, and that's 1/5 times sine of, and u was 1 plus 5t. And if you want, you can add a constant c here. I'm not going to worry much about that. So this is the antiderivative, folks, the one that I boxed here. You see, that's how things work here. So generally, the strategy is, and I'm going to say here, the strategy is, the second type, type 2 of antiderivative in Calc 1, and this is it basically. So we don't learn another type. So that's kind of where we limit ourselves to this. Integral some trigonometric function, function of, some expression, an expression here. Let's put expression times the derivative of that expression. So the expression times the derivative of, let's put here, instead of expression, let's put formula. So let's say formula, derivative of formula. All right, dx, let's say. That is, folks, this is the type 2 of the antiderivative in Calc 1, and that is the calculation that we're going to perform over and over again when we see problems like this. So again, the argument of the problem should be something complex. Otherwise, it doesn't make any sense to, just replace. We have cosine x, replace x by x. What's the point of that? So this is the type of integral that we will see over and over again. You see how that works very well in this case with 1 plus 5t, and it's going to work well in the next example. So that's going to be my last example today. So this is going to be, folks, number 16. Let's do number 16 because it's a better problem. Number 16 of section 4.5. The integral of sine of square root of x divided by square root of x. Now let's sort this out before we do anything. So this is the integral. Let's write it out this way: sine of x to the 1/2 times, and instead of writing here over square root of x, I'm going to say x to the negative 1/2 dx. All right, so look here, folks. Trigonometric function, a formula times the derivative of a formula. Is it really the derivative of a formula? Yes, it is, because x to the 1/2 prime is 1/2 x to the negative 1/2. So up to that 1/2 constant, we really have that. And we are going to see that, again, u equals x to the 1/2. du, what we just said, 1/2 x to the negative 1/2 dx. And look here, folks, there we go. This is the one I need. The one was underlined there, x to the negative 1/2 dx is equal to 2 du. And that gives us the situation that we described here. So sine of x to the 1/2 is sine u times x to the negative 1/2 dx, that we just found out to be 2 du. So we can actually write this as the antiderivative of 2 sine u du, and that's going to be equal to 2 times the antiderivative of sine is negative cosine. So negative 2 cosine will put directly u, and that's going to be negative 2 cosine of x to the 1/2, because u was x to the 1/2. Remember, that's my substitution. So again, folks, it's key what you write here on the left side to work on the right side, plus a constant c if you need that. And I am going to box this formula, and that's going to be my last problem of the day. So my recommendation is, and again, I'm just gonna suggest here to do number 18. Number 18, folks, works by the same way, section 4.5. I don't want to squeeze that here. So quickly here, on 18, the antiderivative sine x times sine cosine x dx. So this is a bit, well, it's a bit tricky here, but you can see that, the argument of sine here, the second sign is this guy. That's going to be your substitution. So u equals cosine x. You can rewrite this thing as the antiderivative of sine of cosine x times sine x dx. So there we go. So almost doing the problem here. Du turns out to be the derivative here. So you see sine of something times the derivative of that thing. So is sine x dx with a minus sign here. So what we'll have here is sine u times negative du. And that is going to be equal to, the antiderivative of negative sine u is cosine u. So cosine u, or in my case, cosine, and instead of u, I'm going to put what u was here. Remember, on the left side, cosine x plus a constant. So cosine of cosine is the antiderivative of this guy over here. That is the answer to this problem. That's, as I said, that's the last problem. I said I will give you a hint, but that's pretty much the entire solution there. All right, folks. So I'm going to stop the lesson here, and I'll stop the recording.